October marks the start of rain that persists until April. For 6 months, water descends from unbroken low clouds. The ground never fully dries. Mosses accumulate on top of each other. Wood left on the forest floor breaks down within a season. Anything exposed becomes slippery, then soft, then vanishes. Nevertheless, in this waterlogged region extending along the Pacific, from Alaska down to Northern California, native people constructed buildings that lasted for generations. These were not temporary shelters or primitive lean-tos assembled from bark and twigs. They ranked among the largest structures in pre-Columbian America, some spanning 40 feet in width and over 100 feet in length. These homes accommodated extended families of 50 or more people. Salmon, intricately carved cedar containers, ceremonial items, tools, and wealth gathered over lifetimes. Such houses could not afford to fail because everything inside would decay within days if moisture intruded. The issue was never if rain would arrive. It always did. The real question was how to. The environment challenged permanence as its core principle. The answer lay in a single tree. The Kwakawakwa called it the tree of life. Western Red Cedar grew straight and tall in the coastal forests. Some specimens achieved 200 feet in height, with trunks 10 feet in diameter. Yet size alone wasn't what made it valuable. Cedar possessed a quality that altered the equation of survival in a waterlogged world. The wood itself resisted decay. This resistance came from its chemical composition, not its physical structure. Cedar wood is infused with natural essential oils, aromatic compounds the tree produces as a defensive mechanism. These oils repel organisms that thrive in constant moisture, fungi that break down cellulose and bacteria that colonize damp surfaces. They also deter insects that burrow into softened wood. A cedar plank left in the rain does not rot the way other woods do. It weathers and turns gray, but maintains its structural integrity for decades, sometimes centuries, while the forest decomposes other materials in just years. This built-in biological protection meant that a house made of cedar required far less maintenance than any alternative. There was no need to constantly replace rotted boards, nor to annually apply preservatives that didn't exist anyway. The material defended itself year after year against the very climatic conditions that defined the region. But rot-resistant wood solved only the first problem. The second was obtaining enough for monumental construction without metal tools. Cedar's grain structure made this possible. Unlike many hardwoods with twisted grain and dense knots, cedar grows remarkably straight with few branches low on the trunk. Consequently, the wood can be split along its grain rather than cut across it. Splitting demands force and precision, but not the continuous abrasive cutting of a saw. It works with the wood's internal structure instead of against it. The technique was exact. Craftsmen used wedges carved from yew wood, a dense, fine-grained species that could withstand repeated impacts without breaking. The wedges were often hardened by scorching their surfaces over fire, creating a tougher outer layer. To cushion the blows and prevent the wedge from splitting under impact, twisted cedar bark was bound to its top. The striking tool was a maul made from stone or carved from antler, and a harvester would select a section of the trunk. Then the first wedge was driven into the end grain, starting a fracture. Additional wedges were inserted along the propagating split, each blow forcing the crack deeper into the wood. When done correctly, the split followed the grain perfectly, producing a plank 4 to 6 inches thick and as long as the log itself. The cut ends were finished with an adze, a hand tool with a curved blade that could smooth the surface and remove rough edges. This method allowed the extraction of massive planks from a log or even from a living tree. Some harvesters practice live planking, removing only a vertical section of the trunk while leaving the tree standing. The tree would continue growing, its cambium layer slowly healing the wound. These scarred specimens are called culturally modified trees, and they still stand in Pacific Northwest forests today. They are silent markers of a harvesting tradition that operated within the forest's regenerative capacity rather than beyond it. The spiritual framework reinforced this restraint. Before taking any part of a cedar, the harvester offered a prayer of respect and gratitude. But this was not decorative ritual. It was understood that improper harvesting, cutting without acknowledgement, would bring a curse from the other cedar trees in the forest. Their cultural beliefs embedded a principle of preservation in the very practice, guaranteeing that the natural resource vital for their existence would be preserved for later generations. This led to a sustainable forestry system functioning at a magnitude that would have needed mechanized sawmills. Elsewhere, findings from digs such as the Muir House near Portland, Oregon, reveal buildings that used many hundreds of thousands of board feet of timber throughout their active years. This remarkable feat of engineering was made possible by understanding the characteristics of materials, not by having more sophisticated tools. After preparing the planks, the challenge was putting them together to form a building that would stay dry inside through months of steady downpour. The framework used vertical support posts and horizontal beams, consisting of huge cedar logs placed upright into the earth or on stone bases, with cross beams joining them. This framework supported the full weight of the building and stayed in position indefinitely, even when the home was taken apart each season. Thick boards formed both the walls and roof, with each board placed meticulously to provide an unbroken shield against water entry. Roof shape was crucial. Northern peoples such as the Haida and Tlingit preferred pitched roofs where two sloping surfaces met at a peak. Around the Salish Sea area, roofs with a gentle pitch were typical, usually sloping only from the front to the rear. Both styles followed one key idea: make water drain away fast. Stagnant water finds gaps to seep through, but water that runs off right away has no chance to enter. The boards were arranged in overlapping rows. Every row was aligned such that water traveling down one board ran onto the top side of the board beneath, instead of falling into the space between them. This offset pattern produced a layered shingle appearance, effectively adding layers of protection. And even if dampness got through the initial layer, it hit another, then another, with each joint directing water down and away. At the roofline's peak, there was an intentional opening, the smoke hole, designed to fulfill two purposes. This opening released smoke from the central hearths that were kept burning constantly, keeping the indoor air breathable, and it also controlled moisture levels. In such a damp environment, humidity builds up within any enclosed area, from breathing, cooking, drying clothing, and simply from many people being present. If there were no air circulation, this indoor moisture would condense on chilly surfaces, encouraging mold and causing wood to rot from the inside. The smoke hole let damp air out, keeping the inside atmosphere drier while rain poured outside. However, the roof only handled water coming from above. A more dangerous problem was lurking underfoot. The soil along the Pacific Northwest coast stays waterlogged for most of the year. The water table lies only inches below ground. Rainfall hitting the earth doesn't soak away rapidly. Instead, it gathers, trickles, and climbs upward. If a building were placed right on this soaked ground, it would take up dampness through its foundation, pulling water up into the walls and floor. Before long, the bottom sections of the home would start to decay, even though cedar is naturally resistant to rot. Raising the structure solved this problem. The substantial uprights and horizontal beams were placed on piles or support columns, elevating the floor a number of feet off the ground. This gap of air interrupted the movement of moisture. Puddles could form under the building, but they couldn't touch the floor people lived on. Raindrops bouncing from the earth couldn't reach the building's lower part. Being raised also boosted airflow, letting breezes pass under the floor and dry any dampness that gathered. The Tlingit people used the space below their raised flooring for storage, making use of an area that would be wasted otherwise. In certain high-ranking Haida and Simian houses, the floor levels stepped down toward the central hearth, forming a recessed fire area. The higher floor around it trapped warmth from the fire and kept sleeping and working areas dry and tidy. This design clearly divided different activity areas inside the home. Raising the building solved the problem of dampness seeping up from below. Yet water also traveled sideways over the land, rushing down slopes during heavy rains and collecting in spots where the ground dipped. A home built in the way of this runoff might suffer erosion under its foundation or have its edges soaked so thoroughly that the building became unstable. This called for local civil engineering, going beyond mere architecture of individual structures. Digs at coastal settlement sites have uncovered complex systems for draining water outdoors. At Ozette, a winter village of the Macau people on the Olympic Peninsula, and at Twat sites on Vancouver Island, investigators found purposeful systems for managing storm runoff. These were intended to safeguard homes from dangers related to water. The most notable instance used whale bones. Whenever a whale came ashore or was caught in a hunt, every piece of it was put to use. The shoulder blade scapulae are big, curved bones that are naturally strong. People placed them vertically into the sandy coastal earth, lined up end to end to make uninterrupted channels. Runoff from storms coming off higher land was caught by these channels and channeled toward the shoreline, steering clear of building bases. This was a significant engineering choice. Plain ditches dug in sandy ground cave in and get clogged with dirt after just a year or two, needing repeated upkeep. Whalebone, on the other hand, is heavy, long-lasting, and holds its form even when water flows over it and soil moves around it. Stable, enduring drainage pathways were fashioned from bones, needing no yearly digging. This infrastructure was constructed from biological materials since they surpassed any other option in the pre-industrial era. Additional findings from Ozette House 2 showed drainage channels beneath the floor, designed to catch water seeping from an adjacent hillside. These channels diverted the water away from the house's interior, keeping the floor supports from becoming saturated. Moreover, elevated ridges of shell midden, built up over many generations of shellfish eating, were placed around the building's edges to catch runoff from the roof. This midden served as a porous barrier, soaking up water and stopping it from gathering right at the house's base, while also stabilizing the ground around it. Such approaches showed a thorough grasp of the site's hydrology. They identified where water would travel during downpours, where it would pool, and how to divert it before it turned into an issue. Despite a dry structure, staying alive required keeping other items dry, especially food and tools. The Pacific Northwest bounty was seasonal and intense. Salmon runs came in predictable surges, carrying huge numbers of fish upriver within just a few weeks. During these runs, communities gathered much more than they could eat right away. The leftover was smoked or dried, then stored for the lengthy months when fresh protein was lacking. A single family might keep hundreds of pounds of preserved salmon, dried berries, roots, and rendered oils. This food had to stay dry since moisture causes mold. Mold makes food unsafe to eat, and without refrigeration, there was no fallback. If the winter supplies went bad, the family would starve. The storage answer was vertical. Open shelves and platforms were built under the rafters, high above the floor. Dried fish, airtight cedar containers, woven baskets filled with berries, were all put on these raised platforms, maximizing the gap from ground dampness and reducing contact with pests like rodents that found it hard to climb to the ceiling. Placing storage close to the smoke hole offered an extra advantage. Smoke from the main fire rose nonstop, enveloping the stored food and preservative substances. This smoke repelled insects and limited microbial growth, providing an additional safeguard beyond mere height. The food was at once kept dry, shielded from pests, and actively preserved by the house's own atmosphere. Sleeping areas applied the same principle. Beds were constructed above the main floor, lifting sleepers away from the cold air that collected at ground level. They were also distanced from any dampness that might penetrate despite the raised foundation. The house functioned with a steady internal rule. All vital items for survival were placed up high, yet the plank house, despite its long-lasting nature, wasn't completely stationary. For communities around the Salish Sea, the seasonal pattern of collecting resources demanded travel. During spring, when salmon started their migrations and shellfish beds opened up, families moved from winter villages to seasonal fishing and gathering spots nearer to the resource areas. Staying in the winter village all year was not efficient. The distance to productive zones was too far for daily trips. The difficulty was creating shelter at these temporary locations without going through the huge effort of building a complete house from scratch. The answer was modular building. The heavy post and beam frames stayed in place at the permanent winter village. However, the thick cedar planks making up the walls and roof could be moved. In early spring, those planks were taken down, loaded into canoes, and moved by water to the summer spots where lighter frames were ready. The planks were put back up, forming a full-size house in much less time than it would take to prepare new lumber. This approach only worked thanks to the sophisticated marine engineering of the Pacific Northwest. The canoes these groups used were some of the biggest and most advanced in all of North America. They were carved from single cedar logs and could haul tons of load on the open sea. The plank house and the ocean-going canoe were technologies that evolved together, each making the other possible. Without the canoes, the planks couldn't be transported efficiently. Without the planks, the canoes wouldn't have any cargo valuable enough to warrant building them. When fall came, the process was reversed. The planks were taken apart, brought back to the winter village, and put back on the permanent frames. The house, which had been spread across several places, came back together, ready to offer shelter during the rainy months. This modular approach revealed a wider outlook. Permanence and mobility weren't opposing ideas, but complementary tactics. The frame stood for a long-term investment across generations and a feeling of territorial steadiness. The planks stood for seasonal adaptability and effective labor use. Together, they formed an architectural system that was both grand and flexible. Still, the house was never seen as just a practical item. It held identity, history, and spiritual force. The plank house thrived not by fighting water, but by managing it. Cedar oils formed a passive chemical barrier against biological breakdown. The slanted roof channeled heavy rain away from the building. The raised floor kept the living area apart from upward ground dampness. The outside drainage system handled site-level runoff before it could endanger the structure's foundation. Indoors, vertical storage kept food and tools away from moisture, and smoke from the main fire provided an extra preservative effect. Each defense layer tackled a different level of the water issue, from the molecular level where wood oils repelled fungi to the civil engineering of whalebone channels diverting stormwater. The system functioned. It accepted that rain was unavoidable and was built for control instead of avoidance. The houses lasted for generations. Certain frames stayed functional for more than a century, enabling the periodic replacement of wall planks as earlier ones deteriorated and were swapped out. The structural continuity reflected the enduring lineage of the families that lived there. Extended families amassed wealth, knowledge, and social influence in the very places their forebears had occupied. When European explorers reached the region in the 1700s, they saw settlements with houses that were bigger than most buildings back home, built without any metal. These structures were designed around hydrological principles that the newcomers failed to immediately grasp. To the explorers, the inhabitants appeared as primitives dwelling in log cabins, and they overlooked the sophisticated engineering. During the late 1800s and early 1900s, the plank house tradition faded. Forced assimilation programs, epidemics, and economic upheaval devastated native communities throughout the Pacific Northwest. Consequently, numerous grand houses were left empty or taken apart. The expertise needed to cleave cedar using wedges, arrange planks for effective drainage, and align a house with the watershed's movement was partly erased when the social systems that passed it down disintegrated. Yet the trees remain. Those culturally modified trees, marked by the live planking technique centuries back, keep growing in coastal woodlands. Archaeological deposits covered by generations of refuse and dirt still contain the whalebone drainage systems and subsurface channels. The surviving or rebuilt houses continue to show what can be achieved when buildings are created to coexist with their surroundings rather than to overpower them. The takeaway is not that cedar is a miraculous resource or that pre-industrial societies held some secret knowledge beyond modern reach. Rather, it is that enduring and harsh landscapes demands a detailed understanding of the ways danger operates. Water is indifferent to human plans. It will seep through any opening, take advantage of every vulnerability, and pool wherever gravity and porosity permit. The sole protection is to foresee the water's path in advance and to engineer each component of the building to channel, divert, or soak it up. The plank house was never constructed to flee the rain. Instead, it was designed to coexist with the rain season after season, generation after generation, in a region where precipitation never ceased and never would. That is the true accomplishment. Not opposition, but adaptation. Not fighting, but mastery. A dwelling shaped by the very cadence of the rainfall.